Hi, welcome to this course about digital twins in the PLC world. You're at the right place to improve your PLC programming skills with the integration of the digital twin. So what will we actually look at during this course? First, we want to explore what the digital twin actually is. I will explain some concepts and we will dive into that in chapter 2 after this introduction. Then we will have a look at why even using a digital twin. So there we will dive into some example, what could be the benefits of applying a digital twin in that example. And in the course of the remainder of this course, we will use this example to simulate, and you will just code along with me in TIA Portal version 18. You should actually be able to do that in other versions as well. But yeah, just the user interface, just for your information, is the TI Portal version 18. And you will not need any additional software, just the default install from TI Portal. And I hope you enjoy. So then continuing with that, we have the simulation in TIA Portal where we will look at how to even implement the digital twin in TIA Portal. And the next chapter after that, the digital twin architecture is related to that, more to the design of how to implement this digital twin. And then finally, we have the how to use the digital twin. And as I mentioned before, we have a use case which you can which we will use to illustrate how this digital twin works. And with that, you're actually able to use this digital twin or a version of it for your own projects to improve the quality of your code and in the end, um, produce better programs, more reliable machines, and thereby saving costs and taking your PLC programming to the next level. In this chapter, we will explore what a digital twin actually is. So let's have a look. What is that digital twin that is so common these days and is mentioned all over the internet and can be quite interesting, as some people say, to software? So a digital twin is actually a model of a physical product, system, or process. This model is a mathematical model, and it actually tries to recreate the product, a system, or a process in the digital world. What it's mainly used for is testing and simulation. As the digital twin is in the digital world, it's more easy to set up and then use, and you don't need any physical system for that. You only need a model and the digital twin itself, and with that you can emulate the reality of this product, the system, or a process. So when we apply that to a PLC control system, just looking at the basics, we have that the inputs of the PLC, they're generated by the digital twin. So everything that's being put in the PLC system or the cabinet, so to speak, is actually generated by the digital twin. So all of the signals that come from sensors or from reality, let's say, physical reality, is now generated in a digital environment. And the outputs of the PLC are actually used as inputs for the digital twin. So the signals that are normally like digital outputs or analog outputs, we feed those to the digital twin so that they can create the inputs of the PLC. As I mentioned before, the model is a mathematical model, and that can be based on physics. So, for example, for a movement application, you could think of some movement formulas and solve those for example, a position that you want to emulate in a digital twin. But as you could also use approximation functions, since the mathematical models can be quite intricate. They can be quite complex, since in reality it always works different than in theory. So it's easier to just approximate a function at first, and then later on you can refine that. But most of the times, if the application isn't really critical, it's best to just keep it simple and refrain to an easy model or just a basic approximation function. So let's explain a digital twin through an example. So in this example, we have an hydraulic circulation process, and we will actually control this through a PLC. And as you can see, it's just an easy application of a water tank, a pump, and a flow transmitter. And with that, we circulate the water. You can see here the arrows, and the pump is just pumping water from the tank. So the water goes from the tank into the pump. The pump pumps it through a pipe, and then we have a flow transmitter that detects the flow. So that's that. And this pump is actually controlled by a variable frequency drive, so that we can determine the flow of the water in here. And with that, we have the complete system. Very basic, but just as an example to get a bit more detail about what a digital twin would be in this case. So what we actually want to do is to have a look at all the components here and the inputs and the outputs for those, so that we can have a look at what a digital twin would actually do. So the water tank has actually no sensors or anything, so there's no electronics in here, therefore no inputs or outputs. Then if we continue until the pump, we have of course the pump itself, and we have the VFD, which is controlled through the PLC. These signals differ, but let's say we have a 0 to 100% signal. We could use analog output for that from a PLC from 4 to 20 milliamps, for example. And that will be a signal here. There's of course some feedback signals as well from the frequency drive, or error signals and that, but we will leave it just very basic. So we have that analog output then, and then the other signal that we have is from the flow transmitter. We actually have an analog input from there. So let's also say that's a 4 to 20 milliamp input. So summarizing, we have an analog input and an analog output. And what the digital twin will now do is take the output of the PLC, which will be the 0 to 100% signal from the PLC to the VFD. So for the speed of the pump. And then we feed that into the digital twin, and a digital twin will actually generate a flow from that. So it will calculate the flow based on some equation of choice. In this case, it could be just having a look at the specs of the pump and approximating the output signal through a mathematical function. You can also make it quite easy with just a proportional output signal. We will of course dive more into that later, but just for now, it's sufficient to just think of an increasing function. So if the analog output increases of the PLC to steer the pump, of course we would expect that the flow will increase. Let's just make that proportional, and that's actually the signal that the digital twin will generate. and the digital twin will give that to the PLC. So the digital twin in this case is just one basic formula. The model consists of that formula, and that is connected then back to the PLC with this flow transmitter signal. So why should we care about digital twins? What is actually the benefit of it? So the digital twin is mainly used to improve your software quality, and that with as less effort as possible. And that's actually what the digital twin is mainly being used for, but let's explore let's get into the details on possible alternatives, as we need to know which alternatives there are in order to assert if a digital twin is even necessary. So some of the alternatives are the physical products system or process. If you actually have the product or the system or the process, you can test on those. So suppose you have some machine, for example, with a PLC, then of course it's possible to test that, and that would be actually quite great to be able to test that on the machine, and then you have actually the best testing environment. Nowadays, that's of course quite hard with prototypes, for example, that are not available yet, or production facilities that are in other countries, and can be hard to have the availability of a machine. And even if you have the machine, it will take quite some time to test some scenarios. It can be hard sometimes if you want to replicate some very very difficult scenario to reproduce physically. It can become quite hard to do that in reality, because you would need to, for example, um, simulate some, well, not simulate, but you need to create some error of a sensor, for example, and that should trigger some scenario, and you want to test that. That's hard because you need to physically create this error. Then, of course, you have manual emulation of signals. That's probably what you've been doing up till now for simulation purposes. So if you're in TIA Portal and you simulate your PLC, you can manually change signals. And with that, so I mean tags and inputs, you can also force them, of course, but mainly by changing these signals, you've probably tested your functions or function blocks up till now. As you might know, that takes a lot of effort, especially for more complex software. It can become quite hard to be in time, sometimes even impossible, because you need sequences or values that need to be increasing or decreasing in time, and you cannot do that manually in time. And just if we look at the example we had earlier, here the simulation of this system would be simulating the input. So the flow, for example, you would simulate that, and then you would look at the PLC program if it gives you some pump signal, so the 0 to 100% signal for the VFD, that makes any sense. But as I've already told before, this is a static change. So say you have a PID controller here for this flow regulation, then you will definitely already see the disadvantages of this approach, as if you give the flow transmitter a constant value, the VFD will just increase the signal as the flow isn't changing, and it should be changing. So that's one of the disadvantages. So summarizing the advantages of the digital twin is that you actually don't need the physical system. So you can do rapid prototyping, at least if you have a model for it, but you can also use this as a a step before testing it on the machine itself. And it can save you quite some costs, of course, if you don't need the physical system. Then, as I mentioned before, you can, of course, simulate the scenarios that are hard to replicate. So think of some error condition that you want to test, and you need to do that physically. Then you would have to probably ruin a sensor in order to test this, which would be a bad idea cost-wise, and yeah, wouldn't be that good of an idea. Then we have the effort. So compared to the manual emulation of signals or tags, as how you prefer, there's definitely less effort as the digital twin is based on a model and it will dynamically respond. So there's no manual intervention there during the cycle. You could, of course, change some parameters manually. That is possible, but that is up to you, and there's some flexibility in this approach. So what are the main disadvantages? The model that is used in a digital twin can be quite complex if you want to make it very accurate. So if you really want to represent reality, it can be impossible, but even just getting to 99% accuracy, there's a ton of modeling effort in there. And that's actually not something that you really want to do. You don't want to spend too much time on the digital twin. As I can imagine, if you don't have unlimited time, you don't want to put that much effort in it. And it's also a bit of a different skill than PLC programming, as you're more involved in mathematical equations and physics. But it can be quite good to see the results of the digital twin in the end, as you're able to really really check your PLC software. So the other disadvantage that we have is that large systems may have many dependencies, and that leads to complex models. So say you have several valves in some pipe, for example. All of these valves could create, of course, turbulence, but that's actually like a phenomenon that you don't want to really touch in your mathematical equations, as it can be really complex to calculate that. But even like looking at the flow, the net flow, there's many dependencies there. If you shut all the valves at the same time, then it can be complex to see what the flow actually is. It really depends on the closing time and all of that stuff. And you don't really want to model something like that, as it can be quite time consuming. The way we want to mitigate those disadvantages is by starting with a low accuracy. So you really want to start simple. You could just have a look at basic physics equations, or you could even use like a proportional kind of approximation of the signal. So with the flow, as I mentioned before in the previous chapter, you can just use a proportional signal for the flow that is being created according to the pump frequency. So if the pump frequency increases, for example, you will get a higher flow, and that's just a proportional effect. And that's actually just great to test some basics of the control logic. So on to the next disadvantage. We want to mitigate that by separating the parts of the system as much as possible. So if you have large systems, just keep it to some part of the system and try to simulate that or approximate that signal as much as possible without diving into all of the dynamics that arise from the interactions of the system. So in the example that I mentioned before with all of the valves, you just want to have a model for one valve and don't look at timing stuff, timing related stuff that can arise from putting all of those next to each other. Just keep it simple. In this chapter, we will explore how to do the simulation in TIA Portal. So all of the previous information or theory of the digital twins, how should we actually implement that in TIA? So in TIA Portal, as you may know, there's a PLC sim also installed, and you can use that part of a software to simulate a PLC instance. And you might not know this, but it supports actually simulating two PLCs at the same time. So you can simulate two PLCs of your project, and there will be no license issues there. And that's actually great because we can use that for simple projects to later on implement the digital twin. So if you actually have more complex projects, larger projects with more PLCs, you can use PLC Sim Advanced. And with that, you can have support up to 16 PLCs. That depends actually on the amount of cores you have on your system. So each simulated PLC will take up one core. So you already need 16 cores to simulate 16 PLCs. But if you agree with me, that would be already quite a complex system with 16 PLCs running at the same time. But it is possible. So the way we want to use our PLC, so if we have, for example, here this PLC from production, we just going to refrain to a basic project where we have one PLC. Here, for example, we have the S7 1500, and with that we just have this PLC card. And what we want to do now is implement the digital twin. And as I mentioned in previous chapters, we have the output signals from the production PLC to the digital twin. So that would be digital outputs, analog outputs, but also things like Profinet and other types of communication. There can also be outputs there. And what we want to get back from the digital twin are the simulated inputs. So that could also be digital inputs, analog inputs, but also inputs from communication. So that isn't restricted to Profinet, but also Modbus, anything that is communication and will be used as an input for the PLC. So how are we going to actually do this? We could, of course, use software like Simulink for the digital twin or other software, but we are bound to licenses then. And we really want to keep it simple also to program with the same, let's say logic with the same programming language. So with ladder or SCL or whatever you prefer, we want to keep it in TIA Portal itself. So we're going to use for the PLC sim install, we're going to use this support for two PLCs. We're actually going to use a PLC, one that isn't actually physical, but it is in the software, and we're going to use that as the digital twin. So that's basically it. The PLC is the second one. We use it as just a simulation PLC, which will emulate the signals from the digital twin. And yeah, with that, you can actually use this PLC, you can add it to a library, and later on, you could also use it for other projects. There's some standardization possible there, but with this, we are actually able to create our own digital twin without any other licenses or any other costs, and actually with really a, yeah, a fast learning curve since you already know how to program a PLC.